hopefully recording. Okay, great. Well, it's nice to be back here and in person and see real humans in 3 dimensions, 4 dimensions if you move around a bit. So what I'm going to talk about today is my research, essentially, and in particular, this kind of slightly mad idea that myself and quite a few other people around the world are working on, which is, why don't we try and map as much of the observable universe as we possibly can using radio telescopes. Okay, so I'm going to discuss a little bit about why you'd want to map the universe in the first place. It's not completely frivolous. And I'm going to also explain why we want to use radio telescopes to do this. So ideally, I'd like this to be, you know, kind of reasonably interactive. So I've got a kind of backbone of a presentation here, but you all have varying interests, varying levels of knowledge about different bits of what I'm going to talk about. So if there's something you want me to focus in on, or you have questions, please just shout them out, and I'll be happy to go over that a bit. Okay, so mapping the universe with radio telescopes. Let's see if the slides move. They just go a funny color. Bear with me. That'll do. So I'm a cosmologist. I'm both a theoretical and an observational cosmologist. So my field of study is the whole universe, its structure, particularly its large scale structure, what it looks like on the very largest distance scales that we can observe, also some that we can't observe, where the universe came from, where it's going, and essentially everything it's made up of. So this is a kind of very, in brief, a kind of why is there anything here at all kind of subject. And what I think you'll see is, in cosmology in particular, we've been able to successfully apply physics to the universe, right? We know that all the stuff we've learned about physics on Earth and in our own solar system actually does apply out there in the universe. And so we can actually get quite far and explain quite a lot about our own universe in the kind of physical and mathematical terms you're all used to studying, which is, to be honest, kind of a surprise. Cosmology was pretty much just a quasi-philosophical, religious subject even until the early 20th century. Okay, cosmology was something priests would argue about, with, you know, not particularly great explanatory success. But at the dawn of the 20th century, some big things happened in physics that suddenly allowed us to come up with a kind of mathematical and physical formulation of the structure of the universe. And the main one, in my mind, is general relativity. That really gave us the framework to explain something that we could call an entire universe. So that's what I study. That's my kind of general area of study. What I'm going to talk about today is really going to focus on the structure part. So what does the universe look like on those large scales? And what was its history? And these are all key ingredients to understanding the full picture. Okay, so you've all heard of the Big Bang. I'm saying this hypothetical origin of time, the start of the universe. If any of you are in the 3rd year and you're doing my physical cosmology module, you'll soon learn that the Big Bang isn't real. It's a useful mathematical fiction. There's actually a bit more of a complicated story about what we call the beginning, but it's, you know, a useful kind of name for the start of things. So there are various reasons why we know there was a Big Bang. The main one being, we see that the universe has evolved over time. We can look back quite far into the universe's history with telescopes and see that it was different in the past. It was smaller, it was denser, it was hotter. This is something called the hot Big Bang model that fits these observations. And so if we extrapolate back, we can see that if you really want to fully extrapolate back, it must have come essentially from a singular point in space and time. Again, that's a mathematical fiction, but this is kind of the picture people started out with. So that's the beginning. We also see where we are now, today, right here. And most of what we see in the universe today, all around us, are galaxies. Lots and lots and lots. Billions, trillions, hundreds of trillions of galaxies. in our observable universe. The reason we mostly see galaxies is, first of all, they're big, they've got a lot of stuff in them, they're quite bright because a lot of that stuff is stars, which are, the kind of predominant glowing things in the universe. Okay, so these are our kind of two endpoints of the history of the universe at the moment. We see what it is today, lots of galaxies, and we have this idea of what it was like right in the past, right at the beginning, this idea of the Big Bang. There's a lot of cosmic history to fill in here, about 13.8 billion years by current accounting. So what I'm mostly going to talk about in the next 25 minutes or so is kind of that history, what we think was going on in this intervening time. So another important point is we don't see anything unless it's emitted, pretty much, right? So I'll just explain why galaxies, they're kind of easy to see because they're full of stars. That's an easy one. We're very used to stars. The sun is a star. We see light from the sun all the time. That's kind of not particularly surprising. But from just after the Big Bang, we also have a source of radiation that we call the cosmic microwave background radiation. And this is essentially a kind of warm glow from the early universe when it was very hot and dense, filled with a soup of ionized gas. That ionized gas later became neutral, gave off a load of radiation, and we can still see that radiation today because the universe is expanding. That radiation has been stretched, its wavelength has stretched into the microwave part of the spectrum. So that's why I call it a cosmic microwave background, and it's almost literally radiation from the Big Bang. Actually, a few 100,000 years after the Big Bang, but it's tremendously informative. It tells us about the conditions in that very early universe. So we know a tremendous amount about the very early universe. And as I've just explained, we know quite a lot about the late universe as well, because we see all these galaxies. We can study them, the patterns they form, the structures that are made up of them. But what about the intervening times? And this is where it actually gets quite difficult. You might have thought that going way back into history would be the more difficult one, but we got lucky with the cosmic microwave background. It was discovered in, essentially the late 60s. It's been studied to death now. Lots of really fantastically precise experiments have made maps of the tiny, tiny ripples in the cosmic microwave background radiation that were imprinted by the structure, the stuff that was there at that very early juncture. So we have a really good view of the earliest times, and we have a pretty good view of the latest times. But what about in between? So you need something to be emitting. You need to be able to see something at those times. And that's where the difficulty lies. So after the cosmic microwave background was emitted, kind of just mentioned, the universe was very hot, dense, ionized, full of a soup of gas, and then it became neutral. Okay, so in the process of becoming neutral, that allowed all of that radiation that was kind of built up, that was kind of pent up at those early times to start freely flowing through the universe, and we see some of that today. That's the cosmic microwave background. But what happened in the universe immediately after that? There wasn't actually much structure. Okay, there weren't any stars, there weren't any galaxies, no planets. There were barely even complex elements. Okay, after the Big Bang, there were just a handful of the most basic elements that were formed. You need more complicated processes to form the heavier elements. So in principle, it was a kind of a boring place, the whole universe, right? All of the radiation has kind of streamed away. All of that ionized gas has become neutral, and it kind of just sits there. So we call this the Dark Ages. Immediately after the cosmic microwave background was formed, this kind of inky blackness where you don't see anything and not much is going on. Now, of course, something is going on, because otherwise, how would you get from there to the kind of complicated stuff we see at late times today, stars, galaxies, stuff like that? Something must have been happening. It may not have been very visible, but something must have been happening. And that thing was gravitational collapse. All this neutral gas that was left over, and also dark matter and other things in the universe, were attracted to one another under gravity, and in regions where you had more stuff, you get more attraction of material to those regions, and regions where you had less stuff, the material would flow away from those regions quite slowly, not enough to form stars or galaxies yet, but it was starting to happen at that point. So this is really, it's very early time when the universe is cold and dark, nothing even approaching the complexity of a star or a solar system. That's kind of the beginning of when stuff started to form. But we call this the Dark Ages. Nothing's glowing. There is an exception. One thing is glowing. It turns out if you have lots of neutral hydrogen, okay, hydrogen is the most abundant element. If it's neutral, it's just sitting there in its ground state with an electron maybe. That emits very, very rarely. Just take one hydrogen atom. It's roughly every 12 million years or so. Then the spin of the electron with respect to the nucleus just spontaneously flips, just randomly every 12 million years or so. And it gives off an incredibly low energy photon. And you can actually work out what the wavelength of that photon should be. And it's 21 centimeters. So by eye, what's that? Does that look 21 centimeter-ish? Something like that. It's less than this and more than this. So 21 centimeter-ish, one wavelength. That's firmly in the radio part of the spectrum. So pretty much the only thing we can see from this period would be radio waves. The problem is the universe is expanding. These radio waves get stretched even more. 21 centimeters is quite long wavelength. It gets stretched a lot. And by the time it reaches us, it's been stretched so much that it's actually below the kind of 50 megahertz frequency. That's more or less the cutoff of the atmospheric window for radio waves. So our atmosphere lets through radio waves to a point, and then very, very low frequencies, below 50 megahertz or so, the atmosphere becomes opaque and starts, reflecting what radio waves. So if we want to detect the radio emission from the Dark Ages, where are we going to have to go? Go for it.
Space.
To space. Except space is a terribly hostile place with lots of other radio emission. So there's a particularly good place we can go, which is the far side of the moon. And this is a genuine proposal to build a gigantic radio telescope in a crater on the moon. Our moon, you don't have to go to anyone else's moon. The reason it's on the far side of the moon is because the Earth is very noisy in the radio. So things like TV, FM radio, global positioning, stuff like that, way, way, way brighter and louder than this faint emission you get from the Dark Ages. Okay, so you want to go to the far side of the moon, find the biggest crater you can, spend a few tens of billions of dollars, and Bob's your uncle, we think we can detect this. I'm not going to talk about that much more today. It's an interesting prospect. It's not as futuristic as it might sound. We think there are feasible ways of doing this in the next order one human lifetime or so. But for now, it's very, very difficult. Fortunately, more stuff happened after the Dark Ages. But we'll never know because Adobe Acrobat doesn't like progressing to the next. There we go. There we go. It wouldn't be week one without technical glitches. It wouldn't be week 8 without technical glitches. The next thing after the Dark Ages, remember, cold, dark, not much going on, is what we very poetically call cosmic dawn. And as you can imagine, this is when stuff starts kicking off. Okay, this is really the period of cosmic history when the first stars and galaxies form and light up. How do stars and galaxies form? Well, I already mentioned gravitational collapse. You have all this stuff, all this material, and after a few millions of years, tens of millions of years, it's collapsed under gravity enough to kind of heat up and become dense enough that you might be able to start processes like nuclear fusion, which is what you need in the core of a star for it to light up. We don't actually know the exact process by which this happens initially. And this is one of the reasons why it's worth studying. We know that the first stars formed. We know roughly when in the universe's history they did form, We don't know the exact details of, how they came about and what those stars would have looked like. There's a particular type of star that we think would have formed in this period. We call them population 3 stars. The reason they're population 3, stars we see today are mostly population 1 and 2. Astronomers love naming things backwards. Population 3 stars were probably gigantic, way, way, way bigger than your typical star today. Very massive, very bright. And because they were so massive and bright, very unstable, and they would have very rapidly gone supernova within, a handful of millions of years. And so this early universe, the cosmic dawn, would have been quite a dangerous place to be around. The few stars that there would have been starting to form would have, don't be anywhere near them at any point, essentially. They're just terribly violent things anyway, because they're so massive, and they're apt to go supernova very quickly. So the very early universe was quite a violent place, but fortunately there weren't too many things in the universe yet. Not many stars formed, not many galaxies. Nothing has had time to form properly yet. You've just got the first few examples of every type of star, galaxy, you name it. It's actually an interesting hypothesis for what could have happened around this stage. So I mentioned when the CMB was formed, the cosmic microwave background, so that the average temperature of the universe around then was 3,000 or so Kelvin. So, really, really quite hot. By this point, the average temperature of the universe has cooled down by, a factor of 10 or so. So suspiciously similar to the melting point of ice. Okay, so there's a very, very, I think, remote possibility that during this small window in cosmic history, conditions all around the universe were what we would call habitable, in the sense that liquid water could exist. The question of whether much liquid water had formed yet, whether there were any, kind of rocky bodies which the water could have formed on, I'm thinking things like asteroids and things like that, seems a little bit unlikely. But this is essentially the first point in cosmic history when life could have survived, life as we conceive it. Okay, so it's kind of an interesting time. It's this first time that the universe could have, in principle, supported life. You've got stars to provide you energy. The temperature's quite pleasant. We're talking Bahamas kind of temperatures for a million years or so. That's not bad. It's a bit violent, lots of supernovae and stuff, but at least you've got entertainment. So, maybe some very short-lived, very adventurous life forms had a brief startup and then terrible catastrophic die-off after this period. Because after this period, oh no, you don't want to be a life form in the universe for a while. But it could have happened. We may never know. It would be very difficult for any organic material to have formed in the first place, let alone survived until now, so we can study it. But it's an interesting thought. So cosmic dawn, the first stars and galaxies light up. Most of the universe is still full of this neutral gas, but around a few stars and galaxies, they're giving off lots of radiation, so they're starting to ionize the bits of gas around them. So the next stage is called reionization. And this is really when the universe goes from being neutral to being ionized again. And now it's not ionized just because the universe is hot and dense as it was just after the Big Bang. Now it's ionized because things are ionizing the gas. And those are stars and galaxies. And so what we can do, and if you haven't guessed yet, it's maybe a little bit hard to see this very dark slide. But this is kind of a representation, an artist's illustration, if you will, of going from early times to later times. And these are supposed to represent bubbles of ionization around those first stars and galaxies. These bubbles are really important, as we'll see a little bit later. These are one of the ways we can study it. But remember, I said neutral hydrogen gives off radio emission, this 21 centimeter line, then it gets redshifted. But in principle, we can observe it. What about in these spaces around the first stars and galaxies? Well, it's not neutral hydrogen anymore, right? It's been ionized, and so it doesn't give off this radio emission. So an interesting prospect here is we look for where there isn't radio emission coming from, and that tells us where the first stars and galaxies were. So in principle, we should be able to find them. Those, almost the very first stars and galaxies, we should be able to find where they were, where they happened from the absence of radio emission at that time. So cosmic dawn and reionization kind of go hand in hand. They flow from one to the other. Then after reionization ends, that's when the whole universe is reionized. There isn't much neutral hydrogen left. Most of your what we call the intergalactic medium is ionized. That's when we start calling it the late time universe, the era of stars and galaxies. And now, if you're human, which I assume most, if not all of you are, this is kind of the most interesting part because it's where you came from, and me. I'm not excluding myself from this. Don't tell them I'm a robot. Robots get paid less. The galaxy era, that's where lots of really interesting phenomena go on. Supernovae, formation of black holes, very large supermassive black holes, formation of planets, spiral galaxies, or elliptical galaxies, all sorts of weird and wonderful things that I'm not going to talk about for the rest of this talk, although you can study those in the radio as well, in numerous interesting ways. So that's kind of a brief history of the universe from my perspective as a radio astronomer. Where can I access this radio emission? What can I do with that radio emission that would let me learn something about physics and in particular the history of the cosmos? And you see it all hinges, again, in my view, in my eyes, on what the hydrogen is doing, whether the hydrogen is ionized or not. If you've got neutral hydrogen, I'm coming for you. I'm going to observe you. So watch out, anyone who's harboring. So now I'm going to talk a little bit about the machines themselves, the radio telescopes, how we build them to try and observe this neutral hydrogen. Okay, and again, shout out if you want to go into anything. So the first thing you need, and this is going to be lots of pictures of twisted looking pieces of metal. I promise you, this thing here is one of the most sophisticated radio receiving devices that's ever been made by humans. It was made just up the road, or designed just up the road by some of my colleagues in Cambridge, some other colleagues at MIT, lots of involvement of other people as well. And yeah, it just looks like a twisted piece of metal. This is very, very carefully designed to give you the kind of best possible chance of very cleanly observing this radio emission, because, as I mentioned earlier, there are lots of other types of radio emission that are in the way. Humans being a prime source of radio emission we don't want to see, but also, from elsewhere in space itself. So you want to very carefully develop one of these things. We call it a radio receiver, and these things aren't like the kind of radio receiver you might have on a car or something like that, where you can just tune into one particular radio station at once. They're simultaneously observing many, 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 many channels. Okay, so the receiver that this is connected to can observe about 1,024 different frequency channels at once. If you're interested in the numbers, that's between 50 megahertz and 220 megahertz. And the reason for that is, if you work out that the hydrogen emission has a wavelength of 21 centimeters when it's emitted, and you work out how old the universe was, so how much the universe had expanded when the cosmic dawn and reionization should have happened, and you figure out how much it should have been stretched, how much it should have been redshifted, then you get numbers in that area. So you typically think of a redshift of about 10-ish, 10 to 20 for the stuff I'm talking about here. So that 21 centimeters becomes about 2 meters, a bit more, right? So you build one of these big receivers, you make it tune into hundreds, if not thousands of frequencies at once. What this means is you can observe the radio emission, not just from one redshift, so one very narrow slice of the universe's history, but many redshifts. So periods when the universe was different ages. So in a sense, you can kind of make almost a video, a kind of 3D snapshot through the universe as seen through this neutral hydrogen. So ingredient one, we've got a really big radio receiver, twisted piece of metal. Now the slightly cooler looking bit of metal that's not as twisted is the dish. So there's a few ways of doing this. The bit you normally see on films with, you know, this parting and a missile comes out and James Bond is shooting there. I mean, you know, we let them do whatever they want with it. But this is the kind of dish you normally see in the films, right? A gigantic one. This is the 500-meter aperture spherical telescope in China. It's quite a new one. As you can see, it's been constructed in a kind of hollow of some mountains. Two reasons for that. One is because where else are you going to build something this gigantic? I mean, it's 500 meters across. It's huge. And two, it kind of shields you from radio emission from cities. So, you know, it protects you a little bit. So this thing is brand new. They're just commissioning it now. They're getting their first results from it. It's very exciting. The problem is it's too gigantic. And so what that means is it can just point at like one bit of the sky at any given time, one very tiny bit of the sky. So you might remember from kind of refraction theory that the resolution of something like this goes like the wavelength divided by the diameter, lambda over d, roughly. So whatever the wavelength is, the diameter is gigantic. And so it just kind of narrows in on a very tiny patch of sky. What I'm trying to do is map the whole universe. So I ain't got 1,000 years to wait for this to map the entire universe, right? I want a different strategy that doesn't rely on having such a gigantic thing. And that strategy also isn't finding hundreds of such valleys and filling them with radio telescopes. If only the funding was available for that, it is not. So this thing's a very nice piece of equipment, but it's not ideal for what I'm trying to do. So the cheap cut price way of doing this is to make a similar sized dish, but from many smaller dishes. And you kind of stick them together in a reasonably clever way. So what you can see here is this is a telescope with a hydrogen epoch of reionization array. We're very heavily involved in working on this at Queen Mary. There's a nice research group of several people working on this upstairs. It's my research group. And we actually work with a bunch of people around the world. A lot of people in the States. There's actually in the Karoo Desert in South Africa. I've got lots of South African colleagues working on this as well, and some people elsewhere. Each of these dishes is about 14 meters across. So they might look kind of tiddly here, but if you put a human next to it, a human would be like that sort of size. So they're still pretty big. And again, some of my colleagues in Cambridge have got a set of 3 of these to do some testing in a field just outside Cambridge. So in principle, you could go and visit them and take photos. But in this field, or should I say desert, barren desert, we'll eventually have 350 of these dishes, all jammed together very closely. Why 350? The most we could build with the money. Seriously, like, once you get to a certain level with kind of experimental or observational physics, the main constraint becomes money and people time. People cost a lot of money as well. So maybe it's people. Anyway, that's by the by. Building this thing is actually, in the grand scheme of things, reasonably cheap. One of the reasons for that is, look at it, look closely, look in detail. This is a telegraph pole. Your bog standard telegraph pole. This is, I'm not kidding, one of the most advanced experiments, one of the most advanced physical kind of receiving devices ever made. These are telegraph poles, not even good telegraph poles, you know, just bog standard cheap ones. And then around here, you kind of have kind of poly piping, you know, just the kind of, you know what a drain pipe might be made out of, that. And then this, any guesses what the kind of dish structure is made of? Not plastic, not plastic. It's got to be reflective to radio, so it is metal. We really pushed the boat out and got metal. Foil. Foil, not a bad shout actually, but foil's too expensive. What could possibly be cheaper than foil? These things are 14 meters across. Really. Too expensive. I don't have that kind of money. You're getting closer, but it's chicken wire. You know the kind of wire you use to keep chickens in a field so they don't fly away? It's chicken wire. So for a while, I mean, this is a lot of chicken wire, to be fair. It's, you know, a pretty major cost getting this much chicken wire. Chicken wire is great because it's easy to shape. The wind blows through it. If it rains, the water just falls through it. If you had something like foil or something like that, you can do that. You can totally do that, but you've got to drain the water away and things like that. So chicken wire, it's very cheap. And because it's radio waves, they're like 21 centimeters or bigger, they don't care that there's holes in it. So yeah, go ahead.
Is this telescope linked to the planetary array?
It certainly is. In fact, this site that you behold in this beautiful photo of chicken wire is actually one of the two sites of the square kilometer array. So they're going to start building nearby the what's called the mid-frequency instrument quite soon, actually. In fact, if you see, I don't know if you can see these just off in the distance, those are the dishes of Meerkat, which is a precursor to the mid-frequency square kilometer array, which is another experiment I work on. It's very convenient, they're next to each other. Yeah, so the SK part of the SK will actually be those dishes as well. 64 out of the 200 will be these things. We're just in the way. They're going to bulldoze us eventually. We just have to hope they, you know, have some delays or something so we can keep going. I'm not even joking. You might see all these really long cables as well. So not all of these have been hooked up actually. I don't know if I can see one. The image maybe isn't good enough. But between these telegraph poles, you string some cable with those fancy bent metal receivers that I showed you earlier. And what happens is the radio waves come in, they're pointing directly up. So you point up, the Earth rotates, you map out a kind of stripe of the sky as the Earth rotates. Radio waves come in, bounce off these, you know, kind of crappy dishes, and then into this very high-tech receiver, and that's how we detect things. And then all those receivers are connected via cables that are just strewn along the desert floor. And what you can't see is where they go into, which is our high-tech, very high-performance processing center. So I'll show you that in a second. We don't just take the signal from each dish, though. Okay, we could do that, and then you'd have a load of very low-resolution dishes looking at the sky. Remember, the resolution kind of goes like the wavelength divided by the diameter. So the wavelength is going to be about 2 meters divided by the diameter, about 14 meters. So you can work out what that is in terms of an angular resolution. It's going to be about, what, 10, 20 degrees, something like that. So very, very blurry image. We can play a trick. And instead of just using each dish separately, we can cross-correlate them. We can take the voltage signal from one dish, the voltage signal from another, multiply them together in a very fast computer, and measure them, and what you get is an interference pattern. It's an interferometer. Okay, so I know you will have all come across interferometry in one form or another before. By this point, we're doing the same thing with radio waves. And by doing that, we can get higher resolution images from a ton of these smaller dishes. And it can be comparable to what you get from one of these big dishes built at great expense in an entire bloody valley in China. We can just have a load of chicken wire connected together and do something similar. Problem is, that's a lot of data. I told you we had 350 dishes, or will have when it's fully complete. It's mostly complete now. COVID has slowed us down by about a year, but it's mostly complete. So 350 dishes. But now we're not just measuring 350 things, we're measuring the product of the signal from each dish with every other dish. So we get roughly 350 squared over 2, which is a lot of data. Multiply that by 1,024 frequency channels. You have different polarizations of the receivers. You're measuring stuff. You know, we take one data sample from each of these pairs of dishes every, you know, few seconds, and you quickly get into the petabytes of data just to sit there and observe. So there's a lot of data that comes from one of these things. In fact, so you mentioned the square kilometer array. That will be even bigger, have even more data. You measure the amount of data that the square kilometer array produces in a day in terms of internets. Okay, like all of the traffic in over the current internet, all those cat pictures, etc. We're going to go into details. All of that for the entirety of humanity. The SK will produce something like that every few hours. Okay, it's gigantic, and we have to do something with that data. So what we do is take Zaki, who was a graduate student at the University of California in Berkeley, really nice guy. We trap him in a shipping container. This is a key part. We trap Zaki in a shipping container with a lot of computers. He's just staying busy here. No, he's doing something very high tech, which is he's pulling together some of the processing boards. So you see all these cables, those cables I showed you in the desert, they are fed into the shipping container. Why a shipping container? It's cheap. But also it's really well shielded. They're metal, they're a Faraday cage. All of this computing equipment would look so bright to a sensitive radio telescope like the one I'm showing you. So bright. So we have to shield it very, very, very carefully. And if someone dislodges a cable or a hole in the container gets bigger than it should do, then all of a sudden everything stops and everything's a big mess. We have to be careful about this. Zaki's fine. After his PhD, he went on to a very nice job, earning lots of money. So he's okay. Don't have to call anyone. He did a great job of, amongst many other people actually, connecting all these things together to what are essentially just networking hardware, networking switches. Okay. And so we essentially have something equivalent to a kind of small supercomputer in these containers. There are multiple containers, processing all this data and reducing them to a more manageable form, and gets piped to Cape Town. It's about an 8-hour drive away from this site, and then through undersea cables makes its way to the National Radio Astronomical Observatory in New Mexico, USA, where it's all put on hard disks, and then people with increasingly numbers of gray hairs like myself and my team upstairs process the data and try and measure this stuff that I've been telling you about. Why the desert? Why are we out in the desert? Because it's miles away. So flying to Cape Town, it's about what, 11-hour flight, 8-hour drive to the site. It's not a particularly fun place to live. You don't see many bars or restaurants out in the Karoo. In fact, it's specifically chosen to be the most isolated part of South Africa, if not one of the most isolated places on the planet. Any ideas why that might be? That's right, radio astronomers hate people. But for a specific reason, which is people generate lots of radio frequency interference. So people have mobile phones, or they would have had pagers, or they drive cars and cars have spark plugs and they give off radio waves. You name it, people will generate a terrible radio frequency signal that gets in the way of everything. So we built this as far away as possible from most people. In the kind of surrounding 80-kilometer area, it's a kind of protected radio astronomy reserve. You're not allowed to have things like Wi-Fi on your house or something like that, which you'd be annoyed about until you realize that like 3 farmers live in that whole area. And they do have spark plugs, but we help them replace the spark plugs when they get, worn and start causing us problems. So it's not a terrible deal, I guess. Plus they're living in the desert anyway. So, but you want to be as far away from people as you can. And part of the reason for that is there are other bright sources of radio emission, but we can do something about those. We can model them, like our own galaxy is one of them. We can model it and try and subtract it. People are very unpredictable. I don't want to construct a physical model for where a farmer is going to drive his Toyota Hilux every morning so I can subtract it. That is borderline impossible without really annoying a lot of farmers. So we need to try and get away from it. Fun fact, another thing that can happen is, wind turbines. So, you know, great source of renewable energy. There aren't any that close to this site, but what they are is essentially quite high above the horizon and rotating. So if you have someone with a mobile phone within kind of an eye line of a wind turbine, the signal from their mobile phone can get bounced off that and over the horizon to us or other radio telescopes, but in such a way that the signal you see isn't just a normal mobile phone signal, it's a very on and off mobile phone signal that looks a lot like aliens. Didn't catch us out for long, but that's an annoying one. Another annoying one that did catch people out for a while, and this was at a particular radio site in Australia. Actually, I think it was at the Parkes Radio Telescope. They saw this absolutely weird signal. It looked artificial, and they'd always see it around, not at exactly the same time, but you know, around the kind of midday-ish or something like that. You know, when the sun is highest in the sky, and you know, there'd be some kind of seasonal variations and stuff like that, but it wasn't really clear what it was. And so, maybe this is something, you know, astronomical, or maybe a new atmospheric phenomenon, something like that. It was the microwave, folks. The microwave at the control center wasn't properly shielded, and so every time someone microwaved a burrito, not at exactly the same time every day, but kind of close, that'd give that just a tiny bit of that microwave energy would leak out and kind of spoil the observations for a while. So no Nobel Prizes for detecting a microwave, sadly, but it's useful to minimize the number of microwaves within the vicinity, which is why you need a big desert. Okay, so I've already mentioned this, but I kind of wanted to show you some pictures. These aren't real pictures, these are simulations. We're still trying to observe pictures like this. It's very hard for some of the reasons I've been mentioning, but now Hera and similar telescopes are up and running. It's finally become a real possibility and might happen in the next few years, I hope. What the telescope sees is something kind of similar to this. So what you can see is the bright areas are where there's neutral gas, the hydrogen we're trying to detect. And then these dark areas are where there isn't any emission. There's nothing coming from there. All of the stuff, the cosmic dawn stuff, the formation of stars and galaxies is going on in those blank bits. So by looking at the size of these areas, these blank bits, these bubbles, over time, so remember we can do this in many frequency channels, so many redshifts, so many different times, you can kind of figure out what the first luminous sources must have been. Were they these population 3 stars? Were they primordial black holes? Were they X-ray binaries? There's a lot of different possibilities, but we can figure that out just from looking at these patterns. Now, it's not quite as easy as just taking a photo or something. I've already told you we're playing some tricks, so we don't have to build gigantic telescopes in a valley every 2 weeks. This interferometry trick comes at a cost, and the cost is it's quite difficult to interpret the data. It's quite difficult to take the data from each pair of dishes and sew them back together into one big image. Okay. They're kind of weird because you're adding things up from many different resolution elements, but it's not the same as just seeing one pixel on the sky like you would with a big dish telescope. You're almost seeing a Fourier mode on the sky. Each pair of dishes is kind of measuring not just, oh, it's bright there, it's not bright there. It's measuring a Fourier mode on the sky and measuring the total brightness of that Fourier mode. So pretty hard to interpret. Of course, we can do this, we'll figure out all the maths. It's a bit fiddly, but we can do it. But essentially, for dishes, for pairs of dishes that are far apart, they see high resolution, so fine detail. So they're seeing Fourier modes with large wave numbers, and dishes close together are seeing the opposite, Fourier modes with small wave numbers. So, you know, smooth, you know, long wavelength sine waves on the sky. And I should be careful of time. I've got another 5 minutes. Yeah. And then we're doing this over time. So we observe for a long time so we can build up the signal to noise. Okay, so this emission is very faint compared to everything else because it's so far away. So we have to observe for a long time, add all the data up to really, you know, integrate down the noise level. We have to remove all these other sources of emission, radio frequency interference from microwave burritos and spark plugs and stuff like that, but also our own galaxy. And then we want to kind of make almost a movie of the structure of this over time. It's not quite a movie because it's not like you're seeing the same bit of the same patch of the same volume of the universe, the same patch of gas at each frequency, at each redshift. You're seeing different patches. You're seeing a slice through the universe. Okay. And then you can build that up and build a picture from it. What can we learn from this? I already mentioned a few things, but the number of these bubbles, these gaps that we see, that's going to tell you what caused them, essentially. Things that are very high energy and very compact can produce big bubbles. Things that are kind of a slower burn, are going to produce slower bubbles with a different shape and size and things like that. You can work all the details out, again, just using physics that we know about from our own galaxy, from even on Earth, radiative transfer and stuff like that. We'll be able to tell how much of this stuff was due to X-rays from extreme stars, these population 3 stars, but even more crazy sounding stars like hypergiants and things that when they explode in a supernova, they form a black hole inside them and other sorts of extremely violent events. Hot massive stars, the first black holes, even maybe dark matter annihilating with itself. Should be a very small signal, but it would change the pattern of bubbles that we would see. So those are some of the things you can tell once you have this map. So I want to give you a couple of holiday snaps, a couple of photos of Hera, just so you can see a bit more of the structure of this thing to conclude, essentially. So this is actually taken from a light aircraft. And you can see that most of this pattern is finished by now, but it's in this kind of hexagonal grid. So if afterwards anyone's interested in why that is, I'll be happy to explain, but it's constructed in this hexagonal grid, all nicely closely packed together. And then you can see just another view of that. This is taken later on, so it's a bit more complete. You can see just how barren and flat the desert is. Again, it's quite a good site for a radio telescope. Not many people. This guy, come on. No, that's one of the site crew. And again, you can see these big dishes that will be part of the square kilometer array. And this is the view from space. Google Maps recently updated their aerial photography of this area. So now you can see it in all its pretty much complete glory. You can see some of the containers there with all the computers in and stuff like that. So it's real, we're observing now. In fact, we started observing again 2 days ago after we fixed some glitches with the computers. So hopefully we'll be able to measure some of this emission from the cosmic dawn and EOR in the next couple of years or so. So I'm really actually just going to skim over this. So I wanted to show you an example of other types of emission that are in the way. This is a map of our own galaxy, taken with a different space-based telescope, Planck. And essentially what you can see, these big arcs here and stuff like that, that's synchrotron radiation from electrons that are spiraling around magnetic fields in our own galaxy that give off bright radio waves at the same frequencies that we're interested in studying. And they're very bright, 1,000, maybe even 10,000 times brighter than the signal we're looking for. So we have to subtract this, our own galaxy. And then I told you humans were problematic. So this is frequency along this axis. And then this is the raw signal, kind of how many radio waves you're detecting as a function of frequency. Guess which frequencies the humans are spoiling. So you see these horrible spikes, and they change with time. They change with, over the course of a day, over the course of weeks, months, years, and they're everywhere. And so we have to somehow chop those out as well. And as you can see, they're very complicated. Yes. So the future, and this is where I'm going to conclude, the future is a square kilometer array. So Hera, Hydrogen Epoch of Reionization Array. This is purpose-built to try and detect the cosmic dawn and the epoch of reionization for the very first time using this neutral hydrogen emission. And I hope we can do it in the next few years. But now, starting this year, in fact, they'll be starting to construct the square kilometre array on 2 sites. One site in Western Australia, again, in a desert, and the other site that we've been looking at quite a bit, the Karoo Desert in South Africa. And this is kind of, again, just an artist's impression of what that might look like. And this time, they want to build so many receivers, so many of these receivers that they've had to design them in this kind of weird Christmas tree pattern. They literally call them Christmas trees. So unlike these dishes we have for Hera, they're even cheaper. Okay, got to be cheap. And they see more of the sky, so there's no dish around them. So they see all the sky at once. That's bad in some ways because if a plane flies over or something, you can't help but see it. But it's good in other ways because it means you see more of the sky in one go. And then they're all combined together in these kind of islands. This is mesh. Can't get away from mesh. Radio astronomers need mesh, called a ground plane on the floor of the desert. That improves the receiving properties. And then this thing that looks like a shoebox or something, that's where all the data processing is going on for each of these islands. And then they're all connected together and strewn across even a couple of 100 kilometers of the desert. So this thing's gigantic. It won't actually be a square kilometer of collecting area in the end, costs too much money, but it's going to be like 0.4 square kilometers or something like that. And with this, we hope not just to detect these signals that we're trying to detect with Hera, but study them in detail, really make a very fine, high resolution movie of the birth, essentially, of the first stars and galaxies. So watch this space, or all of space. Okay, thanks very much for your attention.
Thank you very much, Dr. Phil Bull. If anyone has any lectures that they have to get to, then don't feel bad if you have to shoot off. If not, we've got a bit of time, I hope, for a short Q&A. So if you have any questions on the talk, I'll also quickly mention before that we our next talk is on the 14th with Peter Hobson, Professor Peter Hobson. So do also please come to that. Does anyone have any questions for Dr. Bull?
Sorry, can you repeat? Oh no, just repeat when the talk is.
Oh, check out our social media. It's on the 14th. Yeah, check out all our social media.
Yeah, go ahead.
Earlier on, you were talking about like dark matter, X-rays, and all this. And I've been to a lot of different talks where a lot of these subjects have come up. To me, I've seen a lot of simulations. They all kind of look the same. So, what would you be looking for to try and distinguish between these various hypotheses and what's causing the whole?
Great. So I guess your question. So when we do simulations of how the large scale structure of the universe should look like, they'll look quite similar, but they are different in detail. So on the one hand, they should look quite similar on the largest scales, and the reason for that is because we've measured the cosmic microwave background so well and stuff like that. We have a very, very, very tight constraint on what those large scales can look like. Okay, so those simulations have to reproduce that, but on smaller scales, there's a lot more stuff going on. So by smaller scales, I mean stuff that's smaller than a large cluster of galaxies. So if you want to convert that into numbers, I mean anything smaller than a few megaparsecs, so less than about 10 million light years across. There's a lot of stuff happening there. A lot of what I call astrophysics. So the rest is cosmology. That's all the astrophysics, and you can study that in a lot of different ways. So the most straightforward way of studying it is to look at how much radiation is emitted from each region as a function of time and as a function of frequency. And so if there's more UV radiation coming from it, that's telling you that there are more stars forming. If there's more X-ray emission forming, well, it's telling you something about star formation as well. If there's more infrared emission, it's telling you lots of dust has formed. And so on and so forth. So in detail, if you look at the universe on smaller scales at many different wavelengths, you can learn or kind of work backwards and infer what physical processes should be going on. So does that kind of get towards an answer to your question? It gets even more complicated the you know, if you want to focus on a particular phenomenon, but
So basically, studying radio, but also other types of doing X-ray,
and that's what so much of not just modern astronomy, but modern science is. It's piecing together a picture, a story of phenomena from many different angles. And so, yeah, in astronomy, multi-wavelength studies are absolutely crucial. Some phenomena like the cosmic microwave background, you can get away with just observing in the microwave. And it has a very rich spatial structure. You can see the patterns it forms on the sky. And there's a lot of information in there. Come to my third year physical cosmology lectures for more. But in other regimes at late times, for example, you really do need multiple wavelengths. And in fact, we don't just study cosmic dawn in the radio. I didn't mention the James Webb Space Telescope, which is hopefully launching in December, which can't map out the universe per se, but it can observe individual objects, maybe even some of the first stars and galaxies at this period as well, in the infrared. Yeah, go ahead.
Sorry, it might be a dumb question. But when you were talking about the arrays and they're farther apart, you see finer detail. Now, a bit crazy, but if you had like connected them around the globe, you had in different countries, right? If you connected them all together, could you then get like the best resolution?
So you've just independently invented very long baseline interferometry, which was recently used to observe the essentially the shadow around a couple of nearby black holes. The way we do that is a bit more difficult because so getting all that data, these internet's worth of data across short cables is difficult but doable. Getting that amount of data between continents is horrendous. And so I believe they still have to record the data onto hard drives, like pallets of hard drives, and ship it across to a processing center. Okay, which, if you work it out, if you work all the numbers out, that's a very high bandwidth connection. An aeroplane full of hard disks is very high bandwidth, but kind of inconvenient. So, but yeah, so you can make images, very, very, very high resolution images using that technique, but it's not something you could do. You know, yeah, you have to kind of pick your application of that. Otherwise, it's just it's a big headache.
Towards the start of the talk, you mentioned that this 21 centimeter wavelength was reflected by the atmosphere. So what is it that the Hera detector is seeing? Which wavelength?
Yes, so that's a good point. So if it's highly redshifted, so 21 centimeter line in megahertz, let's work in megahertz, that's about 1420 megahertz, so 1420 megahertz. If that's redshifted down to 50 megahertz or below, which it would be from the dark ages, then that can't get through the atmosphere. But if it's above 50 megahertz, we can see it.
So all this free hydrogen that would have been from the dark age, is that something that Hera can observe, or is that the ones that redshifted out of?
Yeah. So we can just about see the edge of the dark ages. I mean, it's a fuzzy boundary. You might just call it the beginning of cosmic dawn. That's redshift of about 27. If that number means anything to anyone, probably not. But
Is that said?
yes.
Okay.
So redshift of about 27, which is when the universe was a few 100 million years old. So very, very, very far back in time, you know, or over 13 billion years back in time. So very early in the universe's history, but you know, still probably after what we call the dark ages. So we've got to go to the moon. We've got to avoid the atmosphere somehow to really see the dark ages proper.
Are there any more questions?
I'll
ahead.
ask since you almost invited the question. Why is it a hexagon?
Oh yes, excellent. Well, good. I will give you your £20 later for asking that. No. So why is that hexagon? the reason is because if you, first of all, hexagonal patterns, if you've done any solid state physics, you know, it's the most efficient packing pattern. It's how you get the most elements packed together in the most efficient way. And this gives us quite a large dynamic range in the lengths of the baselines, okay, the distances between the individual receivers. So remember, each kind of pair of receivers sees a kind of a Fourier mode on the sky. Ones that are far apart see high frequency, so high wave number Fourier modes. Ones that are close together see low frequency, so smoother Fourier modes. To make a good image, you need a mix of all of different lengths. What we'd say a big range of different baselines, numbers of baselines. So packing things together in this way gives us a nice range of different lengths of baselines. That's one reason. Another reason is how we calibrate the telescope, which is a whole another story, and I could easily talk about that for several hours, which I will do. No, you know, chat to me later if you're super interested. But to calibrate these things, it's one of the hardest problems, right? You receive radio waves, but you need to normalize kind of how much radio wave there is versus what voltage you see. If you've done physics lab, if you've done P lab, you'll know how annoying it is to calibrate things, right? This is super annoying because there are 350 elements all multiplied together and it changes with time and all that stuff. It's made of chicken wire. That doesn't help. So to calibrate this thing precisely, it's quite nice if you have many copies of the same length of baseline. So if you have many dishes, so 2 dishes close together, 2 dishes close together, 2 dishes close together, in principle, they see the same signal on the sky, the same Fourier mode on the sky. So after you've calibrated them, you know they should be giving you the same result, plus or minus some noise. And if they don't, that's telling you something about the calibration. The calibration is wrong or something's a bit off. So that's a concept called a baseline redundancy. And so by building it in this very regular pattern, we can ensure there's lots of redundancy, which lets us check our calibration, which is great. It's still not good enough, but it helps.
Basically, hexagons on hexagons.
If you make a t-shirt, I'll buy it. Great.
Brilliant. Well, if we'll give Dr. Bull another big round of applause.
Very much. Very well.
Please feel free to grab any drinks or snacks on your way out. And once again, please come to the following events. There might be a social in the next week or two, and there's a talk in 2 weeks.